Our next speaker is going to be Onkar Dabeer, who also did his PhD with Professor Masry, and he will get a chance to share with us in some detail his own experiences with Professor Masry. But we wanted to also share this shared interest they developed in discussing mathematical statistics over biscuits and trout at Red Lobster. Tough as Elias was in mathematical rigor, he also made the time for these informal moments where one got to know each other, the human side of these relationships that are so important. But without further ado, let me invite Dr. Onkar Dabeer to share his thoughts with us. He's currently at Amazon, a very illustrious career of his own, went to the Tata Institute of Fundamental Research, was at Qualcomm Research before he ended up most recently at Amazon. Onkar, the floor is yours.
Hello, everyone. It's my honor and pleasure to talk about my association with Professor Masry and to tell you about some of the research that we did together. I got my PhD in 2002 from UC San Diego, and Professor Masry was my advisor. Preparation of this entire presentation has been a trip down the memory lane for me. Of course, my own research interests have evolved quite far from what I did during my PhD. Uh, but nevertheless, there are quite a few invariants, so to speak, that I picked up from Professor Masry. And what I'll try to do is, as I show you some of the high-level snippets of the results that I got during my thesis, I would also like to, share some personal memories of Professor Masry and to uh, tell you about some of the things that I learned from him, which till date I find useful. This June, it will be 20 years since I defended my thesis, and Professor Rao and Professor Milstein might recall the title of my thesis. This was the first slide in my defense presentation. And in fact, throughout this presentation, I'm going to reuse slides from my defense with a few additional notations. One of the motivations for our work was the problem of channel equalization. 20 years back, of course, the 3G wars were still being fought, and 4G was not quite there, so there was no OFDMA, and there was a lot of interest in channel equalization. And whether you did a fractionally spaced equalizer, or if you had, multiple receive antennas and were doing a beamformer, the typical channel model was one of a single input, multi-output channel. And it was common to have a FIR bank to try to estimate the original transmitted signal. If you know the statistics of the data, then the best thing to do is to use the Wiener filter, which minimizes the mean square error. However, in practice, we don't know the statistics, and that's why it was extremely common to use adaptive filtering techniques. The most common of which was the least mean square algorithm, which used some known transmitted symbols to sort of estimate the Wiener filter in an iterative fashion. Of course, in cases such as surveillance where one did not have access to the training symbols, and there were other algorithms such as the constant modulus algorithm, where the aim was to use some prior knowledge about the statistics or properties of your transmitted signals, such as their constant modulus, to try and invert the channel. The LMS and CMA were both very popular, and really the work that I did with Professor Masry was focused on their global convergence analysis as well as performance analysis. Why these problems, right? There's a little story here. When I first started working with Professor Masry, we both had a common interest in using wavelet transforms for doing multi-scale analysis of stochastic processes. But after some initial conversations, we kind of both came to an agreement that the research there had advanced quite a bit, and there was much less room for making a dent. At that time, of course, I was doing a lot of classes on probability theory, and in particular, I was very enamored with some of the new advances that were happening in Markov processes. I expressed my interest to Professor Masry that I was interested in stochastic recursive systems, and he said, you know what, adaptive filters are very common, and they're probably one of the simplest but fairly hard examples to analyze. So why don't you work on those problems and see whether there is something? And that's how we got started with LMS. And in the next few slides, I'll show you, what we ended up solving. The constant modulus algorithm was a slightly different story, and I'll come to that a bit later in the presentation. The general problem we are trying to solve is that we have a desired signal AJ and some regressors XJ. AJs and XJs are assumed to be jointly stationary, and our goal is to really estimate AJ using the XJ. In particular, we are interested in linear filters. An example, channel equalization. AJ is the input to the channel, while XJ is the channel output. Of course, if you know the statistics, if you know the covariance matrix of the XJs, and if you know the cross correlation vector, you can define the optimal Wiener filter. And it is very common in the literature to look at the error WJ, which is the error in estimating the desired signal, assuming that you're using the optimal filter. Of course, the statistics is not known in practice, and that's why in practice we end up using the LMS algorithm. At the top here, I'm showing the equation for one update. But very simply put, the way you arrive at the LMS algorithm is that you look at assume you know the statistics, write down the gradient descent step, and then just remove the expectations and replace them by the instantaneous estimate of the gradient. And you end up with the LMS algorithm. The algorithm itself is more than 50 years old. And at the time when we were working on this problem, particularly the work of Mustakidis from 1998, was perhaps the foremost analysis of this algorithm. So what was really remaining to be solved, right? The main issue in terms of analysis was this, right? There are a couple of simplifying assumptions that were made in these papers, and even more so in earlier papers. And the problem is that even for the simplest case of channel equalization, these assumptions are not met. And really, our goal in this research was that we wanted to eliminate these assumptions, analyze the LMS algorithm, prove its global convergence, find expressions for its asymptotic error, as well as do a transient phase analysis and see whether it gave us any more insight into performance. So we took a different approach to this problem. Our assumption was that the desired signal AJ as well as the regressor XJ are just instantaneous transformations of a stationary Markov process. And we put in a few moment conditions, enforced through some growth restrictions on the functions A and X. But beyond that, there were really no strong assumptions. And actually, this setup is quite general, covers the channel equalization case, but also, covers many other cases, which include, multi-user interference, as well as, correlated interference, and so on. I particularly remember having several very interesting discussions with Professor Masry during this phase. And I think I particularly remember this because Professor Masry often used to reserve these chunks of time in the afternoon for a stretch of 3 hours or 4 hours so that he can sit and sort of dive into the details with me and discuss things. And one of the reasons we made this assumption was, as you're noticing, right, even though this is a problem of stochastic processes, we are slowly shifting attention from random variables to actually these functions E dot and X dot. And the way actually we end up using this in the analysis is that you take the LMS algorithm, when you write its iterations, you end up with a product of random matrices. But now with proper conditioning, what happens is you can start treating those products of random matrices as actually operators on a corresponding function space. And really, so your analysis really shifts to analyzing these function spaces and operators on these function spaces. And that's what really ends up giving the eventual results that we want. And Uh, what happened during this phase was that both me and Professor Masry got very excited about this sort of a transfer, and we went through actually multiple sessions. I remember one session where Professor Masry taught me about the spectral representation, which has, the same sort of, high level insight where you're converting problems about random variables into problems about, functions, and then using those insights to, derive Wiener filters and so on. There's not much I taught Professor Masri during my time with him, but I can take credit for teaching him one thing, and that is reproducing kernel Hilbert spaces. Because, again, even for non-stationary processes, you can start with the covariance functions, and you can define the reproducing kernel Hilbert spaces, and you can use those to actually analyze stochastic processes. So the same overall theme. Uh, but this is just a very typical thing with Professor Masri, right? We used to, while we were focused on research, there were always these opportunities that he used to find to sit down with me and teach me way more than what we really needed to solve that just the immediate problem. So moving on, this is the one of the main results from the thesis. And what I'm doing here is we are comparing the error that you achieve, that you get from the LMS algorithm with that of the Wiener filter. And what the asymptotic result really says is that, this excess error is sort of proportional to the step size. And the exact proportionality constant is really given by this long expression. What is interesting here is that if you look at the prior literature, the second term was missing because of the simplifying assumptions that were made in these. But this second term actually does matter for many applications. And in fact, you will notice that there is actually a negative sign in front of it. The implication of that is actually the following. It was always assumed in the literature that the LMS algorithm can never outperform the instantaneous Wiener filter. But in reality, right, the LMS algorithm is a recursive algorithm, so it's in principle using all the paths. So really, the instantaneous Wiener filter H star should not be a bound on that, right? It's just that this was rarely observed, and that's why the common belief was that the Wiener filter performance is actually a bound. But it turns out that because of the precise asymptotic expression that we have under the most general conditions, you can actually easily start constructing cases where the LMS algorithm actually outperforms. And here I'm showing a simple example of a prediction for an AR2 process where, beyond a particular value of the correlation coefficient rho, the LMS algorithm is always better. But there are other cases. For example, you can look at channel equalization under a strongly narrowband interference, and the aim is to both do channel equalization as well as suppress the interference. And it turns out in this case, you can get up to almost up to 3 dB of gain over the Wiener filter. Our transactions and information theory paper on LMS algorithm has several more results, which I'm not going to go over here, including some results on transient phase analysis. But in the interest of time, let me move on to the constant modulus algorithm. Unlike the LMS algorithm, this is the case where we don't have access to any training symbols. However, the motivation behind these algorithms is the following. Often, particularly in the communication scenario, you know what your symbol constellation was. For example, it's MPSK, and you know that you expect your constellation to satisfy a constant modulus property. So, why not try to find equalizer settings which minimize the variation? And it turns out that actually doing so, at least under ideal noiseless conditions, does result in recovery of the original constellation up to modulo a complex multiplier factor. But this was really the core idea behind the constant modulus algorithm, and just like the LMS algorithm, you take this cost function associated, which is trying to enforce this constant modulus condition, You differentiate it, write down the gradient descent step, and then you replace the gradients with the instantaneous estimate, and that's how you end up with the constant modulus algorithm. This was a fairly popular algorithm at that point for blind equalization. Um, the thing that really stood out was there were hardly any papers doing any performance analysis, or for that matter, even just stability or convergence analysis of the algorithm. Um, and the reasons really were multifold. One was, there is a cubic nonlinearity in the update equation, which kind of makes the analysis very hard uh, because this cubic nonlinearity now gathers through compounds through successive iterations. So it's very really hard to carry that forward. The second is it turns out that the original cost function has multiple minima and saddle points. So the algorithm dynamics are significantly more complex than the LMS algorithm. Uh, I recall at this point, I was very excited, because this seemed like a very hard problem. And I started solving it. And for about 2.5 months, I tried every method that I knew to prove that the algorithm converges. Forget performance analysis, just even proving convergence under some nice simple conditions. I ran a lot of simulations. I tried 3, 4 different methods, virtually everything in the literature that I could find, right? And still there was no success, and I was really beginning to doubt. And Professor Masry had at that point, joked that the constant modulus algorithm was becoming a constant headache for me. But while he was jovial about it, he also actually encouraged me a lot. And in fact, I recall very distinctly that he actually asked me to take a break for a week, right, and come and take a completely fresh look at the problem. And that actually worked. I'll skip some of the details of the assumptions, but really the key assumption here is that assume that whatever noise you have in your system has a probability density. Uh, uh, and really, the main result that we discovered, sort of the twist in the tail, was this. That there is sort of a region for the constant modulus algorithm where if you initialize your algorithm outside of that sphere, the chances that the algorithm is going to diverge is non-zero. And actually what happens is you can make a very precise statement. What you can say is that with every iteration, the norm of your iterates the norm of your filter weights will actually scale by a factor of root 5 or more, right? Uh, and the net implication of this really is the following, right? If you have something like a Gaussian noise, even if you start pretty close to the origin and you have a nice initialization, after a very long time, the algorithm finds its way outside of this region and then, just ends up diverging. So really, this was the twist in the tail. The reason I had such a hard time proving the algorithm converges is because yes, it actually even under very simple conditions diverges almost surely. The almost sure divergence, however, creates a peculiar situation, right? Because even though theoretically under Gaussian noise, the algorithm diverges almost surely, uh, in practice, the algorithm was commonly used. In fact, if you do simulations to see the divergence, you really need to set the value of the initial conditions to be very large, right? So, how do you balance this almost sure theoretical divergence with the practical usability? Uh, and this was something we thought quite a bit about. You don't need to look at any of the notations, but just assume that we have a set H star of Wiener filters. That's the desired set. And ideally, what we want is, irrespective of where we start from, we would first like to enter, this neighborhood of the Wiener filters. Let's call that time as tau j. the first time. And ideally, we would like tau j to be, finite, ideally as small as possible. Uh, and we would like eta j, which is the total number of times that you keep on visiting this neighborhood around the Wiener filters, to be very large, ideally as large as possible. It turns out that with a more thorough analysis, you can actually prove that as long as you start your initialization within a ball of right size, which of course depends on the step size and the tolerances, the probability that you enter this neighborhood of the Wiener filter in a finite time is actually greater than 1 minus epsilon. And you can also show that the number of visits to this small neighborhood uh, is actually very large. In fact, our conjecture was that the bound I have here is very loose, and really, the number of visits is going to be probably exponentially more than this. We were never able to prove that convergence, but this is sort of the redemption, right? Yes, under the most common communication system models, this constant modulus algorithm actually diverges. So it's very hard to, find compact expressions for its asymptotic error. But in reality, it's still useful because if you initialize it properly, it does with a very high probability enter the neighborhood of the Wiener filters, and it does spend a lot of time there before eventually you see these large deviations which you take you into the instability regime. I continued to work with Professor Masry even after I left UCSD. We wrote a few papers after that. One was on diversity analysis and its different applications in wireless communication systems. Another one was on signal parameter estimation using only 1-bit samples, and sort of dithering plays a significant role there. Um, my own interests have evolved, and in fact, the last 6, 7 years, I've been spending more time doing computer vision and machine learning, and heavily into this deep learning era, managing applied science teams at Amazon. But there are some invariants that I mentioned at the start that I learned from Professor Masry, and I think I take them with me, and just wanted to share some of these with you. I think one thing that I learned from Professor Masry was never to compromise on quality. He was a stickler, he was a perfectionist who paid attention to details. And I recall after the first work on LMS algorithm, we started writing our submission to transactions of information theory, where the paper was eventually published. But that draft took me such a long time because I slowly learned from Professor Masry the importance of every comma. And just getting all the notation right and everything right. For him, everything had to be perfection. The other thing I really took from him, and I hope I do it for my own team, I'm doing it as well as he did it for me. He was a really devoted mentor, and he always had time for you. He was always eager to spend time with you, and used to reserve these 3, 4 hours slots where we used to sit, get into details, and talk about all kinds of things on our common shared interests. Uh, it is something that I had a great time when I was at UCSD for my PhD, and I think some of these sessions that I had with Professor Masri are the most memorable. Another thing I learned from him is to strive for the right abstractions. Of course, Professor Masri loved analysis, right? So he always liked to take on the challenge of proving something under the most general assumptions. But there was actually a pattern there. It wasn't really generality for generality's sake. And at least, in the work that I did with him, right, he constantly wanted to have this balance where you're general enough to be widely applicable, but still not still wanted to make sure that whatever results we come up with, right, there is actually intuition behind those. And in fact, I recall on I think it was for the LMS algorithm. After I got those asymptotic expressions and showed him all of these examples where the Wiener filter beats, etc. I remember actually he went on and wrote his own Fortran 77 code, to check some of that, right? So yes, he always loved to take on a good analysis challenge, but it wasn't just abstraction for abstraction's sake, right? He was always keen to also have equally get insight into the actual problems. And the other thing I learned from him is to take on hard problems. Don't be afraid to take on hard problems. Be steady and be patient, right? I think that has really carried me further in life. All these things that I've learned. I have had my own journey where I've transitioned different during through different research areas, and I think a lot of it has to do with the strong fundamentals that I received from Professor Masry, as well as some of these behavioral aspects that I learned from him. So my heartfelt thanks to him, and I'll remember him forever. Thank you.
Thank you very much, Onkar. I remember my conversations with Elias, but listening to you and Dharmendra and Professor Bolo, I can kind of see how consistent he had been. He wasn't just espousing his views, he practiced it. I was wondering if you had any additional thoughts you might want to share with us live.
Yeah, absolutely. As I look back, right, I met him first in 1998. And if I were to sort of have these flashcards, right, of my time with him, a few stand out very, like, I still remember my very first meeting with him. He actually gave me a photocopying card. He said, this is your friend while you're at UCSD because you have to copy lots of paper and you have to read lots of papers. And indeed, I made great use of that card. Then these I already mentioned these afternoon sessions. Somehow he always liked to meet me in the afternoon and reserve these 3-4 hour slots. Those are sort of imprinted in my memory. I also mentioned our dinners at Red Lobster. Just like Dharmendra mentioned, right? Like he liked cheese and hated chocolate. I think if I remember correctly, he also hated garlic. So virtually every time we went to Red Lobster, he would make a request, and the waiters probably knew him because they would actually make a fresh batch for him with no garlic. Uh, so so that's another thing I remember. I actually kept on even after I left UCSD. I kept on coming for ITA, and I used to visit him every year. My last time I met him was 2013, and my only regret is that Professor Masry and I we were planning that we'll meet together and he'll get to meet my family. And I think he fell sick, and somehow that meeting did not happen. So he never got to see my wife and my son. And after that, I also moved around, and unfortunately, we never met. So that's one regret I'll always have, never having him meet my family. But I received a lot from him, and will be, I feel, indebted to him, and forever remember him.
Thank you very much, Onkar, for sharing your thoughts with us. Very memorable. Thank you. Not many people spend time proving divergence. So a few more testimonials, and then we have some special announcements from our dean. This is from Professor Tara Javedi, who recognizes, as we all do, how genuine a scholar Elias was and how compulsive he was about the proofs. And at the same time, the tough love that we heard from Professor Buller, truly fun to try to write a proof with him. Thank you, Tara, very much for sharing your thoughts. Sweta Sarkar, who was a PhD student or worked in networking when she was here at UCSD with Professor Cruz, currently on the faculty at San Diego State, took Professor Masry's queuing theory course. And I think many students who worked in networking remember him for that. And she says that to this date, she remembers his unique style of teaching, where every word that he spoke in the classroom was also written on the board, and how as a professor now, it's difficult for her, and how deep an appreciation she has for what he did as a teacher. And she wishes him peace in his heavenly abode, from Sweta.